Hi everyone, my name is Van, and I'm a senior chemistry major in Dr. Rebecca Thompson's lab, and today I will be presenting on the effects of protein absorption on self-assembled monolayers. There it is. So essentially what we're trying to do here is optimize surfaces for biological uses, and one of those biological uses is medical devices in the body. And all medical devices that go into the body come in contact with blood and must experience something called thrombus formation or thrombogenesis. So thrombus formation is the aggregation of platelets on a foreign substance and kind of just the blood coagulation mechanism that happens in the body. So specifically what happens is that a device enters the body and a lot of proteins absorb on the surface, and that triggers platelet aggregation, thrombin, and all of this leads to inflammation, which leads to device rejection. So if we were to increase the biocompatibility of the device and increase the longevity of the device in the body, we must find a way to prevent thrombosis from happening, and we can do that by decreasing the amount of absorption of blood proteins on the surface, so this initial step right here, so that devices can last longer in the body. And one way we can do that is by using albumin-coated surfaces. So albumin is another plasma protein, and what is unique about it is actually it reduces platelet adhesion, and so now there's less protein absorption on the surface, which lessens the chances of inflammation and increases the biocompatibility of the medical device. However, this technique is not perfect because the albumin desorbs from the surface over time, and scientists have been trying different etching methods and thin films to elongate the life of albumin on the surface. However, those are also not perfect because they deabsorb over time as well. So if we could increase our understanding about what's actually happening molecularly and atomically, we can better understand what is happening at the surface and at the protein, at the site of absorption, and better optimize medical devices in the body. But how do we look at such small interactions of like a protein on a surface in a really complex system like the blood? And we can do that by using self-assembled monolayers. So self-assembled monolayers, or SAMs, are organic materials or organic molecules that spontaneously fix on a surface. So spontaneously, in fact, and how we make them is we just put gold in a solution of our organic molecules, and after 24 hours, they will self-assemble into a monolayer. What's also great about SAMs is that they're extremely customizable, and so we can change the length of their alkyl chains, so the carbon chains, to be really, really long or really, really short, and we can also manipulate the end group of our SAMs right here to be different function groups, different proteins, different antigen. And what's really great about the customizability is that we can put in variables or take away variables in our experiments when we are ready to deal with them. And so what this does is that it allows, we can use SAM to simplify really complex systems like a protein absorption in the blood, and we can just focus on the core interactions that are happening at the site of absorption. And so, how do we characterize SAMs? And we do that by using PM-IRAS, or polarization modulation infrared reflection absorption spectroscopy. It's a really fancy name, but it's still just a spectroscopy method. So what happens is that light hits a molecule, the molecule gets excited, and we see it in a spectra. What is unique about this technique is that we get structure and orientation information, and it does that by being selective towards surface normal dipoles. So what happens here is that the light that exits from the spectrometer is propagated in a p-polarized direction, so it's perpendicular to the surface right here. So it excites dipoles that are perpendicular to the surface, and that's how we get orientation information, because if the dipole was somehow slanting different ways, we should be able to see that in our spectrum ideally. Another method, this is what it looks like in real life. So we have a series of mirrors that hit our sample holder and goes into our detector. Another method is called a QCM, or quartz crystal microbalance. And what it does is that we put the crystal in a device and it's connected to a circuit, and when electricity goes through the crystal starts to vibrate. And so, as we put mass on the crystal, the vibration changes, and the change in vibration, or the frequency, is related to some constant that is equal to a mass. So using this equation, we can find out how much mass is on the surface using the change in frequency of the device. However, we have found that this equation may be too simplified for us, but I'll talk about that later. And so our system right here, what we're using, what SAMs we're looking at, is MUD and DDT. So MUD is a 11 carbon long chain with an OH at the end, and DDT is an 11 carbon chain with a methyl group, or just a 12 carbon chain. And the protein we're using is bovine serum albumin. So it's an albumin protein, but like the first few slides. And so, but it is derived from cows, that's what the bovine is for. And why we're using MUD and DDT is that they're really simple SAMs, like we're only changing the head group right here. Another reason is that we have a lot of spectral data on these SAMs, so it can really guide us in our preliminary experiments. So what we're testing in this our system is how the hydrophilicity of the surface affects protein absorption. So our initial results shows us that we can actually see our SAMs on the surface. So MUD, so this is similar to the last slide with MUD. However, I just abbreviated the carbons, however it's as long, it's still 11 carbons long with the OH at the end. And what we see here is the vibrational stretching, symmetric and asymmetric stretching of the CH2 molecules, which is the backbone of the SAM right here. And the reason we don't really look at the OH peaks on the SAM, because OH is really common in the atmosphere, so even if we see it in the spectra, it doesn't mean that is the OH on our SAMs. And so our next SAM is the 12 carbon long SAM dial right here. And as you can see, we're looking at 4 different types of stretching. We're looking at the asymmetric and symmetric stretching of the CH2 and the asymmetric and symmetric stretching of the CH3s of the methylene group. And then what we did in the middle here is we did a combination of MUD and DDT. And so we're going to look at, so we do the same thing where we look at the asymmetric and symmetric stretching of the backbone and then the methyl group. And so these are spectra before BSA absorption. And so let's look at what it looks like as BSA is absorbing on the surface. So how we did that is we put our crystal of the SAM in our QCM, and we initially run water through the QCM to get an initial frequency of what it looks like before BSA absorption. And then I connected the inlet to the BSA solution, and this is when BSA starts absorbing onto the surface. And as it starts to plateau, I connected the inlet back to water, and as you can see, although there's some increasing again, there's still a big difference in frequency between before and after BSA absorption. And so that means that BSA is not leaving the surface, and it's having some connection to the surface, and BSA is having some electrostatic or absorption in the surface that is stronger than the water that's flowing through it to get rid of the excess. And so this seems that there is some irreversible protein absorption that may be happening on the surface. This could also mean that the protein is being immobilized on the surface. And we see that protein absorption happens in all 3 different vials as well as the different types of SAMs. And so what this data is telling us, this is a conclusion of what we saw here, but in just in numbers. And what we're seeing in the first trial is that MUD has the most absorbance of BSA compared to the other vials. And what this may look like is that ESA has an isoelectric point of 4.7 to 4.9 pH. That means that at this point it is neutral, However, we link BSA in water, which is around a neutral pH. And since BSA is in a neutral pH environment, the overall charge of BSA is actually negative. However, what we found is that BSA actually, while it's negative, still absorbs to negatively charged surfaces. It's not because it's like breaking any like physical laws, it's because there are positive residues of amino acids in BSA that remain positive when it's at a neutral pH. And those positive residues are what it's attaching to a negatively charged surface. And so we can theorize that maybe the different polarization and partial charges of the OH and this negative group right here is causing BSA with its positively charged residues to absorb more on FBT than it is in DBT. Okay? However, in our second trial, the trend kind of changes. MED is no longer the SAM that absorbs the most protein. It tells us that maybe the mixed SAM is actually absorbing more protein. And so this leads us to different conversations. And what we did was we compared our QCM with the spectral data. So now we're looking at BSA peaks on different SAMs. And what we do is we look at two different peaks that are related to BSA, the amide-1 and the amide-2 peaks. So we look at the amide-2 peaks, which is known to quantify the amount of BSA that is on the surface. It kind of tells us that it seems there's the same amount of BSA is on different SAMs, which may be true if the error of these calculations are within error of each other. We could look at the amide peaks, and that could be telling us that. However, the amide-1 peak, there's a little bit of a discourse between what it's used for. Some people say it's used only for conformation of the protein, and it can't be used for absorption or like to quantify absorption. But other people have used it to quantify absorption. And we look at just amide-1, it kind of tells us the trend of trial 2, where MED has the most BSA absorption, and then the mixed SAMs, and then the TBT, which we saw in trial 1, but not trial 2. And so there's some discrepancy between the PM layers and the QCM data, which we're still trying to figure out. And one last thing is that now we're back to the SAM peak, so we're looking at what SAMs look like. So the solid line is the MUD, and then the dotted lines is the MUD after absorbed BSA. And as you can see, the peaks are actually shifting to a higher wave number, and this may indicate that the SAM is becoming more disordered. And what that may look like visually is that without BSA absorption, the SAM can kind of vibrate freely as it is excited by the laser. But with protein absorption, it's kind of being squished to maybe a different conformation, and that's why it is absorbing at a different wave number. And so, to kind of summarize what happened here, is that we were able to characterize the SAMs using the PM rares and the QCM. And with the PM rares, we were able to distinguish that there was protein on our surface, and we were able to distinguish between different SAMs that we were using. However, we're still working on the cohesiveness between the story that the PM rares is telling us and the QCM is telling us, and that may mean that we need to find a more rigorous way of calculating error for the QCM and maybe realigning our spectra as well. However, we were able to do what we set out for, is looking at those really small interactions between the surface and protein absorption. So this is from trial 2. Yeah. And so if what could be happening is that the amide-2 is telling us that there's the same amount of BSA that's on the surface, and that our QCM data may be all within error of each other, and so they're maybe absorbing the same amount of protein. Yeah. However, it could be that our child 2 is an outlier on what the Miss Sam is saying, and that this amyloid 1 peak may be telling us that MUD is absorbing more. Oh, sorry, BSA is absorbing more on MUD. Any questions? Yeah.
So what is the peak at the 1427 kind of tells us? Why is it that it's saying that the previous one is higher and absorption for that? What is that really saying?
Yeah, so this is the scissoring of the CH2. So, let me picture this again. So it's this part, right? So they're going like this. And literature have been saying that usually this peaks indicates how straight up the SAM is standing. So it kind of tells us about the orientation and disorder. So we could theorize that maybe a higher peak means that it is more ordered and it is more straight up and packed well. And so if this is more ordered than all of these other SAMs, it may be saying that because it's more ordered, there is more BSA generally there. So maybe our QCM data is telling us that there's more BSA there. However, it would be interesting to see what these amyloid peaks would look like if this peak right here was at the same absorption as the other two files, just to see if the same orientation of the CH2 scissoring would affect BSA absorption.
I have a question. I don't have the correct vocabulary to ask it.
Yeah.
So you have the picture where you had your kind of squished stand.
Oh, yes. This one. Oh, no. This one.
Yeah.
Yeah.
So is it typically that one protein binds per molecule, or do they like bind?
No, so like, BSA is actually very, very big, so I just drew it like this to kind of show you what's happening, because SAMs are small, really small compared to the protein, so it's probably several, maybe one protein is in like several parts of the SAM. So it's not usually one protein, yeah. Yeah.
So in your introduction, you talked about using albumin to try to prevent thrombosis from happening. Why albumin specifically? Are there any other proteins that could be options?
Oh, yeah, so first of all, albumin is something that's already present in the body. So if we were just to utilize it in like a specific area, like the surface of a medical device, would probably decrease the chances of rejection. Infection fluids are pretty within the body, and we're really used to ourselves, we're probably used to it. And so what it does is that it prevents platelets from aggregating on that surface. So if there's less platelets aggregating on the surface, there's less chance of it causing an inflammation and then less chance of it rejecting device rejection. Yeah.
Any other questions? All right, so let's take a pen again. And give her, so we're still on the words.
Okay. What do I do?
Say something nice.
Okay. Well, I'm excited. I wish. What happens to this?
So she'll wear those during graduation.
Oh,
Here's the first.
well, here, this is in. And I want to thank you for your time in our lab. Dan is one of the first students to join my lab. So we're graduating my first seniors this year, including Avery, who's going to come up next after Dan. And without the two of them and their one partner, we would not be where we are today as a research team. Dan has helped us get organized. She lifted that QCM off the ground. That was a brand new instrument that she figured out how to use and is still figuring out how to use. So Dan has been really instrumental here in the chemistry department. Thank you for all the